On the Rigol DSA 815, what you see is a depiction of the return loss of a high-pass filter, mini circuits high-pass filter. I'll show it to you in a little bit. But it is set with the using the tracking generator, a level of minus 20 dBm, and then a minus 32 dBm reference level. And what you see is very little return loss up to the frequency. This is a 250 megahertz filter, and then the return loss gets very steep. It's minus 50 dB here, dBm, and it stays down below about 46 dBm up to the midpoint. This is a 1.5 megahertz on the right, so this is about 750 megahertz in the center. So up to about 800 megahertz, it's below, it's more than, or below minus 46. And then it rises up to around minus 42 out at 1.5 gigahertz. So why am I showing this? We've done return loss measurements on other stuff before. Well, what I would like to do today is to compare the use of a return loss bridge with a directional coupler for doing the same thing, and talk about some of the advantages and disadvantages of each. Now, the return loss bridge that I'm going to be using is a relatively low-cost bridge that I bought from a company called 60dBm, and their site is 60dbm.com. I think I paid $7 for it, including shipping. It came from China. And the directional coupler that I'm going to be using is one manufactured by Mini Circuits. So let's take a look at a little bit about directional couplers and reflection or return loss bridges, and then we'll get into the measurements. So here is a reflection bridge or return loss bridge, and we'll talk about the bridge in a second, but basically a return loss bridge consists of an input port, that is a place where you can apply a signal, two branches, one that is connected to the device under test or the test port, and the other is connected to a reference. Now in this case the reference is a pair of 100 ohm resistors in parallel, or 50 ohms. By the way, the reason that they often use a pair of 100 ohms is 100 ohms is a standard value, 47 ohms is the next closest. If you used a single resistor, 47 ohms is the closest you could get. So they use two 100s because that allows you to get as close to 50 ohms as you can measure. Notice that the connection from the signal source to this point on that side as well are also pairs of 100 ohm resistors. So it's basically 50 ohms here, 50 there, 50 here, and then from the test port to ground is whatever the impedance is of the device under test. Then you have a structure here that often confuses people. Don't worry about it. It is basically a balun. That is, it's really an unbal, because it goes from an unbalanced signal source here to a balanced source so that you can read the output port relative to ground. Notice, by the way, that there is a DC path from the test port to the output port down the center conductor of this coax. There is no DC path from the input port to the test port because the input port is connected to the shield of the coax, both through these 50 ohm resistors and through this 50 ohm resistor to the shield of this coax. The shield of this coax is grounded, so that means that the and I think that's actually a mistake. That's not supposed to be grounded. I never saw that before. But at any rate, this is a design that I found on the web by VE2AZX. I've never actually built this, so I don't actually know whether it works with this or without it, but actually what this would do is, since this is shorted here, it would actually short that to ground, so I'm not sure this is right. At any rate, what I would like to do, though, is draw effectively what's going on here. There's a signal source that's coming up here, and then there's a 50 ohm resistor coming down to these points. Then there's a 50 ohm reference. This is the reference, and this is the device under test. And then this, of course, is ground. And then what you're doing is you're measuring the current between those 2 points, or if you put a resistor between those 2 points and measure the voltage across it, you're getting the effective, and that's why it's called a reflection bridge. Basically what it's doing is you apply power to the input port, and you measure power at the output port, and it will, by measuring the power at the output port, what it will tell you is how much power was absorbed by the device under test. In other words, the power goes in here, gets reflected, and comes back here. So, for example, if this were a 20 dB, if the return loss was 20 dB, that's basically 100 to 1, and you put 100 watts in here, you would get 1 watt reflected here. And by the way, that's also an SWR of about 1.2 to 1. And I'm sure that you know that there's a direct relationship between return loss and SWR. You can download charts about that if you're interested. Let me now switch and talk about what a directional coupler is. It's a little bit different device. A directional coupler has a direct connection from the input to the output. These are SMA connectors, and you notice that the grounds are connected together through this the copper on the board, and then there is a strip line from this connector to that connector, which is a direct connection. So if you forget this part at the bottom, basically this is just a straight through connection. What the strip line at the bottom does is, because it's very close to this, notice there's a very small gap between the two, it picks up or couples some of the energy going through this, or power going through this strip line. And you can then measure the forward power and the reflected power. Now, often for a return loss bridge, the forward power is simply grounded through a 50 ohm resistor, or terminated through 50 ohms, because you don't really want to measure the forward power, you want to measure the reflected power. So this is often just grounded to 50 ohms. But directional couplers come in 2 flavors. They come in a 4-port like this, where you can measure both forward and reverse, but remember that when you're measuring reflected, you have to terminate the forward. When measuring the forward, you have to terminate the reflected. The particular return loss or directional coupler we're going to be using is made by Mini Circuits, and it's a 3-port. It has an input, an output, and a reflected port, but the forward port is terminated in 50 ohms internally. The device that we are going to use for the device under test is a 225 megahertz high-pass filter. It's called a BHP 250 Plus. It's made by Mini Circuits, It has a 50 ohm impedance. That means that the input as well as the output are matched for 50 ohms. And it has a pass band from 225 megahertz to 3000 megahertz. So what we were looking at a little bit ago was the return loss of this device. So let me show you the hookup there. And while we're at it, the one reason we're going to be using this is because we have some pretty good test data that's been measured by mini circuits. And of course this is typical. Each unit will vary slightly, but basically this is what you can expect. On the left is the frequency range. In the middle is the insertion loss. In other words, how much gets lost from the input from one end to the other. The next one is the one we're most interested in, the return loss. And then over on the far right is called group delay. We aren't going to be concerned with that, but that becomes very important if you're trying to process pulses through a filter. Okay, let's look at the setup. Okay, here is the setup using the return loss bridge. This is a little return loss bridge manufactured by 60dBm.com, and I bought it from China. I think it was about $6 or $7, maybe $8 anyway, less than $10. At the top is the reference port, and I've got that terminated with a 50 ohm load. On the left is the input, and this comes from the tracking generator of the Rigol DSA-815. On the right is the output, and this goes to the spectrum analyzer input of the DSA-815. And then down here is the device under test. I've got a little adapter to adapt SMA to BNC. Then I've got the filter, and then I've terminated the other end of the filter in 50 ohms. We'll look at what happens when you don't do that in a minute. That's rather important. So essentially what we have is, on this side of the filter, we have exactly the same impedance as we have on that side of the bridge. What is what you see down the middle is the ferrite beads that form the balun that we talked about earlier. So let's take a look once again at what we got on the Rigol. And here again you see the very little return loss. Once again, the reference is at minus 32, and we're reading about minus 32 is, and the tracking generator output is minus 20 dBm. And then at the reference frequency, or the 225 or so megahertz where the filter begins to pass signals, the loss goes way down here. Now, a lot of people get confused by loss. Remember, we're talking here about you send out power, and the question is how much of it returns, or how much loss is there. Think of it like standing on the bank of a canyon with a sound meter, and you shout while watching the sound meter, and let's suppose that you get 50 dB of sound, and then you point the meter at the echo, and suppose you get 10 dB back. That means you had a 40 dB return loss. The 50 you sent minus the 10 you got back is 40 dB. That's what return loss is. Now we're doing the same thing, making the same measurement, but using a mini circuit's directional coupler. Notice that I have changed the reference level slightly. Instead of minus 32, it's now minus 35 dBm. But we get the same effective response. Notice, however, that the response out above about 700 megahertz or so is a little more uneven, let's put it that way. And we'll talk about that in a little bit. But we see the same thing. The reflection, or the reflected power, or the return power, is pretty high at this point, then the returned power drops way down, or in other words, the return loss goes way up. A lot of power is being absorbed at the other end of the filter by the 50 ohm load, and far less of it is being reflected back. And that is at the filter frequency. And then above the filter frequency, you see what you have here. Now, some of this is due to the connections that I use, although I'm using the shortest connections I have and the best cables that I have. In a real metrology lab, we would expect that this response would represent only the response of the filter. But here, what you're seeing is partly the response of the filter and a little bit the response of the setup. So let's look at what that setup is like. And let me turn some light on this. Hopefully you can see what we're working with here. Here is the bandpass filter with the 50 ohm termination at the top, connected through a BNC to N connector into the mini circuits. The mini circuits is there, perhaps hard to see. Let me turn this off, see if that makes it a little easier. The mini circuit's directional coupler is this device. The output of the directional coupler is connected to the tracking generator by this cable, and the input is connected to the spectrum analyzer input. Now you may think, well, that's backwards, and it is, but remember, we're looking to measure return loss. We're not looking to measure forward power. So this is the setup using the return loss bridge. So in a minute, I'm going to repeat the same measurements using the mini VNA Tiny Plus that I reviewed earlier, and then perhaps we'll go look at it on the Siglet. The reason I'd like to use the mini VNA Tiny Plus is I'd like to see what happens when we get out to 3 gigahertz or so. And that device will go out there. So will the Siglet spectrum analyzer and tracking generator. So let's take a look at that, and then we will talk about the relative advantages and disadvantages of using a return loss bridge versus a directional coupler. Before I go to that, I did tell you earlier that we were going to show you what happens if you remove the termination. So I'm going to do that now. And you see what you get. Remember now, the other end of the filter is open. And so what we are getting now is essentially a transmission line, an open circuit transmission line. I'm going to put the 50 ohm load back again. And you see we get what we really expect. And if you want to think about that for a minute, here is the point. With the 50 ohm load, it absorbs most of the power in the pass band. In other words, after the filter begins to pass the signal, the reason that this signal does not get reflected is because it's absorbed in the 50 ohm load. So if you don't load it, the power is all reflected, and of course it varies in frequency depending on the length of the transmission line and the particular frequency. But that's the reason why you need to terminate things like this while you're measuring them. I'm over on the VNA Tiny Plus, the vector network analyzer that I reviewed a few videos ago. And what you see on the screen is the return loss in green and the impedance in ohms in blue. The reason I'm showing this is I thought I would point out, mentioned earlier that how important it is to have a 50 ohm termination, but I didn't mention that it's also important that your 50 ohm termination be a good 50 ohms at the frequencies of interest. In this case, we're going up to 3 gigahertz on the right and starting at about a megahertz on the left. You notice that we have a lot of return loss here at down in the few tens of megahertz. By the time we get to 500 megahertz, the return loss is only minus 24 dB. It remains a little around minus 20 or so dB out to here, where the return loss becomes a little greater, a little above 2 gigahertz. This is 2 right here, and then goes back up and winds up at about minus 16 dB at 3 gigahertz. Notice what's happening to the impedance of the 50 ohm load. And 50 ohms is this line right here. So it's remaining relatively, well, it's within, the one above it is 63 ohms and the one below it is 38 ohms. So basically call it plus and minus 10. And you see it stays fairly within that plus and minus 10 range. Now, let me substitute a different 50 ohm load. And now this is, the one I'm using there is an SMA dummy load, or 50 ohm load, with an adapter to convert it to a BNC. Now is just a straight BNC, and we're going to run a single scan on it. And you notice what we're getting. Not only does the return loss go up quite a bit, particularly above about 2 gigahertz. Remember we were at or below minus 16 the whole way on that other load. We crossed minus 16 here at just above 1.5 gigahertz. And this is fairly typical, and by the way, here is the resistance. Once again, this is the 50 ohm point. Stays within 50 ohms until it gets out to about 1.5 gigahertz, where the return loss is starting to go above minus 16, or in other words, less than minus 16. I realize that using negative numbers for return losses, it's one of these things that's debated in the community, which is right. But so you would probably say that you wouldn't want to use this 50 ohm load above about 1.5 gigahertz. Notice, by the way, that when it gets out near 3, the impedance is up, well over 130 ohms. So 2.5 to 3 times what it should be. And that's important. Now we're going to switch over and hook up the filter that we were looking at using the return loss bridge and the directional coupler, and see what it looks like here on the Mini VNA Tiny Plus. Okay. As you see, pardon bumping the camera there, the return loss is virtually zero until we reach the filter frequency, at which point it goes down with a little bit of an anomaly there, but pretty much down to about minus 47 or 48 dB. Then it recovers a little and goes down again, and then it starts doing this. What that is resonances, or I should say quarter wavelengths of the signal. In other words, what a lot of us in the metrology area used to call the plumbing leaks, because they're basically a result of open or shorted a quarter wave and half wave sections, which at these frequencies can be down in the centimeters The impedance of the filter, you notice, is well over 127 ohms here, drops down to practically zero at or near the resonant frequency, and then recovers and eventually comes back to around 50 ohms, and then oscillates around 50 ohms there. Now this is typical of a filter that is designed to work at a low frequency, and they don't pay a lot of attention to how it works at the higher frequency. But if you remember, we looked at that spec sheet, and it said that this one was good out to 3 gigahertz. At least it implied it, because it said that it's a high-pass filter from 225 to 3,000 megahertz. There's 3,000. Given that the impedance of the filter varies quite a bit, particularly when you get above about a gigahertz. Once again, I would rate this filter as probably a good filter up to about 1 to 1.5 gigahertz, but probably not above that. So now let's take a couple of return loss measurements here, and I'll compare that. I'll just read from the performance data that Minicircuit states. At 150 megahertz, the insertion loss that Minicircuit states is 30 dB. So let's go to 150 megahertz. There it is. And the return loss magnitude should be 0.62 and we read 0.30. But that's okay because that's in the pass band. Now let's go up to the 250 megahertz frequency range. There it is. And it says the return loss in dB is minus 25. And Minicircuits, well, Minicircuits only gives it at 225. So let's go down a little. That's about it. Minus 27. And Minicircuit says it should be minus 23. So that's fairly close. But now let's go out to, say, 700 megahertz. And we're reading minus 34 dB. And Minicircuit says 28 dB. That's pretty close. Let's look out here at near this peak. That's about 1.4 gigahertz. Let's use 1 gigahertz. About there. 1 gigahertz, it should be 29.79, and we get minus 21. So we're a bit off there. Now let's go out to 2000 megahertz. minus 25, and it says 27, and then 3,000, it should be around 16. And it's minus 12 and a half. So, not exactly as many circuits specifies, but remember, these are typical performance data. They're not guaranteed. So what I would say is that the filter is close enough. It's not good enough for use in metrology or any place where you need a highly accurate filter. But for general purpose applications, it's close enough to the typical performance data that I would say it's I trust many circuits, and I think they're probably pretty close. The main idea, though, is the idea of measuring return loss using a reflection bridge or a return loss bridge, or measuring it using a directional coupler. So let's talk about that and then close all this out. Here is the setup that we've just been using. Of course, this is the USB cable to the computer, mini VNA Tiny Plus. The DUT, or device under test, is connected through an adapter to a BNC, and the reason is this mini circuits filter is a BNC filter. And then on the other side is another BNC to SMA adapter, and then an SMA dummy load. Now here is the dummy load that I was using. It is a BNC dummy load, and I'll just an aside here. In general, while some well-made BNC connectors can go out to 2 or sometimes even 3 gigahertz, the average off-the-shelf connector, particularly the lower-priced ones, you really can't trust much above 1 to 1.5 gigahertz. And so it doesn't surprise me that we are getting some anomalies here, because none of these are metrology connectors or adapters, and certainly this filter is not intended to be highly accurate. It's intended for general purpose applications. And so what we got in terms of specs is probably typical for general purpose equipment. So now let's take one last look at the difference between a directional coupler and a return loss bridge, and then talk briefly about where they're applicable. As you recall from earlier, a directional coupler has a direct connection from its input to its output. And in fact, you can reverse them and use this as the input and this is the output, as long as you remember to reverse the coupled ports as well. Why would you prefer a directional coupler in certain circumstances? Well, number one, it has a DC connection, and that means that if, for example, you are powering the remote device over the coax, you need a direct DC connection from the power source to the device. So a directional coupler will work in that case. Depending on the wiring, a reflection bridge may not. Also, because you have a direct connection, you can generally leave a directional coupler in the line. So if you need to make continuous measurements under use conditions, in other words, say that you're having to measure the return loss or the reflected power in a broadcast station that's on all the time. Well, you can't afford to be removing the feed line to insert a return loss bridge, measure it, and then hook it back up again. Because if your station operates all the time, that's more downtime, and you want to minimize that. So those are places where you might want to use a directional coupler. There are problems. Because directional couplers have this, what I will call the plumbing problem, it's very difficult to design a directional coupler that will work over a wide range of frequencies. We work equally well over a wide range of frequencies. And so there are some that are quite good, and they're proprietary designs, and they operate with, generally though they do not release the designs. You can take them apart and discover that they contain all sorts of tricks to generate a wide band coverage. But in general, directional couplers are pretty good over a fairly average bandwidth, say from a gigahertz to 2 gigahertz or something like that. But when you get out near the end of the extent of the plumbing, you do have some problems. On the other hand, return loss bridges can often be designed for very wideband. It depends, and this is a slightly different design. It's basically the same as the one we looked at earlier with the input here, 50 ohms. Uses 100 ohm resistors in parallel once again to get 50 ohms. This is one side of the bridge, this is the other side. This is the unknown impedance side. This is the reference side. You may remember when we looked at the one that used ferrite beads, the reference was internal. On this one, the reference is can be changed by the user. So you don't have to use 50 ohms. You could use 75 ohms or 400 ohms or whatever you needed to use. Now, obviously, if you change the reference impedance, you should change either these resistors and your signal source, or account for the fact that you're using a 50 ohm source and a non-50 ohm reference. Finally, the balance shown here are toroid balance, but the ferrite balance that's shown here is equally useful. In fact, over a wider frequency range, often the ferrite balance work better than the toroids. And the reason is that the toroids, the capacity between windings of the toroids tend to cause resonances that can cause you issues. But at any rate, reflection bridge is generally a superior method in that it produces slightly more accurate results usually than a directional coupler. But because it can't be left in the line permanently, and because it cannot provide DC power to the unknown, notice that the signal source here has no connection, no DC connection to the measured impedance. And for that reason, if you're having to power the device, then a directional coupler is preferred over a reflection bridge. So I hope that this has been useful to those of you that are considering buying or using a reflection bridge. I've been trying to find low-price devices that can be used for RF measurements. The mini VNA is, depending on where you buy it, somewhere between $400 and $600, say an average of $500. This noise source, which you can use in place of a tracking generator, is about $20. This reflection bridge is $7 or $8. The mini circuits directional coupler that I showed you, it's a good deal more expensive. I think if I remember right, it's about $80 or $90. You can use any source And you can use the noise source with a reflection bridge like this and a spectrum analyzer like the RSP spectrum analyzer that I've also been reviewing. So the purpose of this is to talk more about what is a reflection bridge, what is a directional coupler, how can they be used to measure reflection loss or return loss, which can be translated directly into short standing wave ratio. I hope it's been useful to those of you that are considering or maybe have used some of this and would like some ideas about ways that you can expand or add to your capability for measuring RF. At any rate, look forward to some videos in the future, and in the meantime, have a nice day.